the mic. It's my great pleasure to introduce Inti Sodemann, who is giving a condensed matter seminar today. And the subject of his talk is on the board, but let me say a couple of things about Inti. So I first met Inti while he was still a postdoc at MIT. He was a Pappalardo fellow, and prior to that, he was actually in Texas. He was at UT Austin working with Alan McDonald.
Oh, you're Alan student, I see. So you
yes, I'm local.
Nearby, it's very local.
And then, since then, he first was a group leader at the Max Planck Institute at Physics of Complex System. And, in fact, when I advertised the talk, I haven't realized he's already moved. So the new position, he's a professor at the University of Leipzig. So Inti has worked on many interesting topics. He gave an invited talk at APS, which is different from what he's telling us today. But anyway, the subject of today's talk is going to be about the Spinon Fermi surfaces. Great pleasure.
Thank you very much, Andre, for the invitation. It's my first time to come to Rice, after being so in such proximity. So it's really great. It's been really nice visit. Thanks a lot, Andre. Thank you all for coming. So today's talk is going to be about chasing, the Spinon Fermi surface state. Okay, it's a very interesting state of matter, and there is some recent experimental evidence that I find very, very provocative for the presence of this state in a material, but with a very interesting twist. Okay, it's not going to be the same Spinon Fermi surface that Anderson introduced. It's closely related, but it has an interesting twist, I think. Okay, so very briefly about myself, as Andre was saying, I was just at the Max Planck Institute in Dresden. I was there for a few years. This is a very beautiful institute in a very beautiful city in Dresden. It's, if you wish, a German version of KITP. Okay? It's like a German version of Santa Barbara. So it's a great place for conferences, for various kinds of visits, short-term, sabbaticals. If you're ever interested in, having a nice time in Europe, check the website. There is, postdoctoral positions. You can submit proposals for conferences. It has various modes of trying to visit the institute, and it is an institute thought for conferences and for visitors. So that's why I say it's a kind of German analog of KITP. And I am still affiliated to the institute. I have right now a sort of partial affiliation that will go until more or less the end of this year. But I have recently moved to the University of Leipzig. Okay, so Leipzig and Dresden are sister cities, very close to each other, 1 hour by train. If you're ever around the area, please let me know. It would be great to have you. It's a place of a lot of history, very interesting history. It's a place where Heisenberg was a professor and where he spent his golden years. Okay, that's where he won the Nobel Prize, and he trained PhD students. Some of the founders of solid state were trained as PhD students by Heisenberg Leipzig. And he was there really during his golden years until the moment he went on to lead the atomic bomb project during the war. So I am at the Institute of Theoretical Physics, but there is also a couple of sister institutes there, Peter Debye, Felix Bloch Institute. So wherever in the area, please let me know. Right, so now physics. So the talk is basically divided into 2 parts. So first is going to be some kind of introduction to this traditional version of the Spinon Fermi surface state, which in itself is a very quite non-trivial state, and maybe potential evidence of where it could be and how to look for it in experiments. Okay. And then the second part of the talk is going to be focused more on a specific material, alpha ruthenium chloride, where I want to make the proposal that there is good evidence for a new version of this Spinon Fermi surface that is not the traditional one that we could call the pseudo-scalar Spinon Fermi surface state, although it has some close relation. Okay. So the Spinon Fermi surface state, let me introduce what this state is. Okay, it's a state that, you know, was basically the pioneering ideas came from earlier work by Anderson. And so the idea is that it's a fractionalized state of matter in which the electron breaks up into two emergent particles, a fermion called the spinon, denoted here by F, sigma is the spin label, and some boson, that sometimes is called the chargon, that is spinless. It doesn't have spin. Okay. And so this is the Slade boson factorization of the electron operator, which is a convenient language to understand this state. You know, it's a Parton construction, so it comes with an enlargement of the Hilbert space. So here R is the lattice size. Imagine we have our electrons in some lattice, sigma is the spin. And so the physical states are only states in which, you know, you are created by the action of the physical electron operator. So every time you add an electron, a fermion, you have to add a boson. So physical states need to satisfy this constraint that the total number of fermions at each site equal the number of bosons at that site, and the lowest must equal also the number of electrons, which are the actual physical things. These are just some kind of variables. They're not physical. Really. They are some convenient variables to understand the essence of the state. Okay. And so what is the state about? So imagine you have some lattice, okay, some tight binding, Howard tight binding like model at half filling, okay? Meaning for simplicity, just imagine you have some Bravais lattice with sites R, and then the spin label sigma, and so there is one electron in average per site at each site of the lattice, half filling, because you could have two by the spin, right? Then if you have, you know, some kind of simple dispersion for the electrons, because you're at half filling, you would have a Fermi surface. Okay, you have to fill half of the state, so you will be forced to have a Fermi surface. And so the Spinon Fermi surface state is a state in which this piece of the electron, the spinon, makes up a Fermi fluid, a Fermi liquid state, Fermi liquid-like state, and the chargons freeze. These bosons freeze into a mode insulator. Okay, they are localized, whereas these ones are itinerant. They are forming a Fermi surface state. Okay, yeah. So a good trial wave function for this state is a state in which you put the fermions, the spinons, into the, you know, the Slater determinant of the Fermi surface, the free Slater determinant of the Fermi surface state, times some trial state that you have for a mode insulator, for a bosonic mode insulator. So the chargons can, by the way, form the bosonic mode insulator because they are filling one, right? So you have one chargon per site, so they can just freeze, right? And there's no degree of freedom left from the point of view of the chargon. So a good trial state is a product of this free fermion and the chargons, and then times a Gatzwiller projector that just brings you back to the physical subspace. So you remove from the wave function everything that does not satisfy the constraint. That's a good trial state. That's a picture of what this state is. Okay. This Slade boson representation is very useful for understanding the mode transition, the mode metal insulator transition, which is a continuous phase transition from this Spinon Fermi surface state to an ordinary Landau metallic Fermi liquid. So the Landau Fermi liquid is a state in which the chargons are both condensing; they are itinerant still. Okay, the fermions are, the spinons are in the Fermi surface, and the chargons are itinerant. Okay, that sounds weird, but it's just a, you know, a language or a set of variables to understand an ordinary Fermi fluid. You can convince yourself that this is just the usual Landau Fermi liquid. So that state of both condensed chargons, and then at some critical point in which the chargons undergo some mode insulator to superfluid transition in the insulated inside of the chargons, then you will have the Spinon Fermi surface. Okay, so it's a very nice language. It allows you to understand usual metals and also
So
this-
does crystal structure play a role in determining whether it's a liquid or it's a metal or insulator in the charge or whatever charge long?
Yeah, so the lattice, you must be in a lattice in which you should be, at least for the traditional state, there is various variants, but this is the simplest.
Mhm.
You must be in a lattice in which you have a filling so that there is one chargon per side, so you can just freeze it naturally, right? So the chargons localize.
So it can
They
be so the
insulate.
square lattice will work.
Yeah, the specifics of the lattice for the possibility of the existence of the state
Mhm.
will be okay. A different question will be, is it the ground state of a given Hamiltonian, or maybe does the Hamiltonian, orders into the triangular lattice and Heisenberg antiferromagnet? But from the point of view of is the state of constructable in that lattice, it's fine. Doesn't really matter whether it's triangular or square, let's say. Right, so what I gave you is sort of the mean field picture of the state. Okay, there's one important ingredient that I did not mention, that this Gatzwiller projector, okay, the one that is really bringing you back to the physical space, introduces really very strong quantum fluctuations on that mean fieldish state that is just the Mott insulator of chargons times the later determinant of Fermi, okay? And that projection is the one that gives rise to the emergence of a gauge field. Okay, the gauge field is basically the object that is taking care of the enforcement of that Gatzwiller projection into the physical state. Okay, so the gauge field tries to enforce this constraint. So these particles, these spinons, and these chargons, they are not just really this free product state, really. They are very strongly coupled by this gauge field. Okay, so that gauge field in this particular case is one gauge field, so it's like, it's like a photon. It's an emergent photon, okay, like the one you have in QED in 2 dimensions. Okay, it's a 2-dimensional photon, okay. And so one of the important consequences of this, strong chargon-spinon interaction, in a sense, by the constraint by the gauge field, is that all the physical states need to be such that there is the same number of local density for the spinons as chargons. Not anything that deviates from that is not physical. And so when the spinon, because the only thing that can move physically is the electron. Okay, so I'm here kind of cartoonish. The blue dot is the spinon with the spin, and the red ball is the chargon. So when an electron, which is this composite, moves, they must move together. Okay, the spinon and the chargon must move together. Okay. So this constraint effectively also enforces the constraint that the physical particle current of electrons must equal the particle current of the spinons, and that must equal the particle current of chargons. They have to move together, okay? Because otherwise you would violate the constraint. If you just hold the spinon without the chargon, you will be left in a physical state. So any kind of physical fluctuation of some initial state that you had by some perturbation, by some dynamics or whatever, has to be such that this is satisfied, okay? But as they move, as they hop, they can have, in a sense, different phases. Okay. So, the electron, let's say, as it hops between 2 neighboring sites, might acquire some phase phi, phase of the electron. But the constraint or the condition is that that phase must equal, the sum of the phases of the spinon and the chargon. Okay. And so you could think of the phase of the physical electron appearing from, essentially Peierls substitution from what it picks up from the vector potential, okay? And so the idea is that that phase will split up into 2 pieces, okay? One that is the one that the spinon is acquiring, and one that the chargon is acquiring as it hops. And so the emergent gauge field, the emergent vector potential that I'm denoting here by little a, so this capital A is, your physical electromagnetic field that you put in the lab into the system. And this is the one that emerges in the material. That emergent gauge field is really just keeping track of the differences of the phases, okay, that the spinon and the chargon are acquiring. Okay, it's a device to keep track of this difference, of this phase difference. And so these, in the end, you can convince yourself. So there's emergent gauge fields and emergent electromagnetic field. So there will be an emergent electric field, I denote here by little e, an emergent magnetic field, in addition to the the ones that you are applying in the lab, the capital E and the capital E. And so, but this splitting of the phases as the electron moves, you can translate it into a splitting of the forces. Okay, splitting of the fields. It's just very. If I make this splitting of the phases that the spinon and the chargon are acquiring, then the time derivatives of those splittings of the phases will be related to the electric field. So you can convince yourself that the forces, the electromotive forces that the spinon and the chargon experience when you apply the physical field, the capital E, will also be different as long as the electron, as they adapt to the force that the electron is experiencing. And they have here a common velocity, as you notice, which comes from this constraint that they must have the same current. They must move together, okay? So again, this little emergent field are keeping track of that difference of electromotive force, how the physical electromotive force splits up into the one that the spinon and the chargon experience, okay? And so just doing those kind of, intuitive analysis, you can derive some result that, this you can derive with more sophisticated methods. I just want to give you the intuition, right? But you can derive a very important rule for how to compute the physical conductivity, so the actual thing you measure in the lab, from the conductivities associated with the state that the spinon has and the one that the chargon has, which is called the Joffe-Larkin rule. And the rule is just that the spinon conductivities add up as inverses. So the physical electrical conductivity, the one that tells you how much is the total current of electrons in response to the electric field, is given by the sigma. And so just by combining, that statement that the spinon current equals the electron current, the chargon also equals the electron current because they are moving together, but they experience different electromotive forces, right? Because of this splitting of the phases. Just with this intuition, do a little bit of algebra and you will get this, okay? So it is as if they would add as resistors in parallel, okay? And this gives you the intuition why the chargon, when the chargon is a superfluid, remember that I told you that's a usual metal. When the chargon is both condensed, you are in a usual metal. So if you have a resistor and this is a superfluid, all the resistance is in the spinon, so it behaves like a metal. In fact, it's the resistance of the Fermi surface, the thing that is making the Fermi surface. When this is an insulator, then this can have a large resistance. So the drop of the voltage is there. And so then when the physical resistance changes dramatically when this thing is condensed or making an insulator. Yeah.
So when you're thinking about the gauge degree of freedom of the chargon and the spinon, in the case that the chargon is both condensed, how do you account for the sort of broken ion symmetry in that superfluid phase?
At this level, all you have to do, right, is compute what people would call proper conductivities, right? So the idea is, this is sort of a mean field picture, okay? But the idea is this sigma c, which is the conductivity of the chargon. You just open up your textbook, pick up the electrical conductivity of a superconductor, and plug it there. Okay, so that will contain implicitly the gauge breaking of gauge invariance, but this is a physical gauge invariant object, right? This is the physical conductivity. You know how much, when I apply an electric field to a superconductor, how much physical current flows? It's a gauge invariant quantity, but it depends on the nature of the state. So if you plug that here, and here you plug the one of a metal, the statement I was making is that the full resistance will just be metallic. Okay. But for the spin on Fermi surface, then you need to plug here a insulating resistance, the resistance of an insulator, of a Mott insulator of those bosons, of the chargons, and then the total will not be metallic anymore because it will be dominated by this part. Okay.
Sorry, can I? So if I think about the system in this force picture you give here, but then at the next time step, wouldn't the velocity of the three particles be different?
That's a constraint.
That's
So I'm not allowed to break it because
okay.
that's part of the constraint of being in the physical phase.
Okay, so they are like tied together.
If they move
Okay.
together, no, if one moves faster, then I could find suddenly pile up of a Spinon density here without corresponding piling up of charge, so the state would be unphysical.
Yeah, right.
So it's a constraint. You could think of this as it's coming from the gauge field. The gauge field is at strong coupling, so they are always flowing together in some sense.
Okay. Okay. Thank you.
So very good. So it will give you this Joffe-Larkin rule. And look, you can make a living with this Joffe-Larkin rule. Lots of really non-trivial and interesting things just follow by doing this Joffe-Larkin rule carefully. I've written several papers with just in the end, the essence is this Joffe-Larkin rule. It's really powerful. Okay. Yeah. So this is basically what I was saying, that if the chargons are superfluid, they will sort of shunt the resistors. So you will get metallicity, get a lot of charge flow. If the chargons insulate, the total conductance will be sort of dominated by the chargon, which will be insulated. Okay, so the spin on Fermi surface state is an electrical insulator. The conductivity of the state as temperature goes to zero and the clean limit goes to zero, and frequency goes to zero. All the usual things you would do for an insulator. To define the static DC conductivity, it will look insulated. The static DC conductivity is insulating. And this one is metallic. Let's say this is in the normal method. The thermal conductivity will always be metallic because of everything contributes to heat transfer. So here, you have a metallic-like thermal conductivity. Here you have a metal, so metallic thermal conductivity. So the spin of Fermi surface is an electrical insulator that behaves like a thermal metal. Okay.
Oh, would you expect a gap in the spin channel?
No, it's gapless.
Also, this is the model naturally comes always to be gapless.
Yes, because the Spinon has a Fermi surface and it still carries the spin. So all the spin excitations are still gapless. Right. So, this, as we were talking a little bit at the beginning, this state has been around, it's been controversial. There is various materials that people have proposed and maybe it's still under debate. So let me just highlight a few. So, one sort of material that has some reasonable evidence to contain a spin-on Fermi surface state are these triangular lattice organic materials. One of the strong indications of the presence of the state is that it displays this metallic thermal conductivity, so linear Inti thermal conductivity, even though it looks like an insulator and with no sign of conventional magnetic order to the lowest temperatures people can measure. But there is other, few materials that have come up over recent years, just to highlight a few, this is still very under debate, but it could be that mixed valence insulators have some variant of the state. We can talk about that, but I don't want to get there.
Samara Hexabor is very controversial.
Yeah, Samara Hexabor is very controversial. I would say this one has a higher chance of being of not killing the hypothesis too easily.
Are there experiments to show the oscillation as well on this?
This one has oscillations as well. I just didn't copy but this one has oscillations of the magnetization and also some oscillations of the resistivity that look like you have insulating behavior, but on top of the insulating behavior, some kind of addition of an oscillation. Okay, and this one, the thing that makes the Samarium Hexabor, I think, tough to defend the spin-on Fermi surface at the moment is that there is no very clear evidence for linear in T kappa. Whereas this one does have linear in T kappa and it shows the oscillation. So here I think it's a little bit more promising. Okay. And but there is other materials. Right. So one of the really crazy things, and this in part is related to the same kind of intuition that I was telling you, is that the spin on Fermi surface state, even though it's an insulator, it can display quantum oscillation. So when you apply a magnetic field, there's some kind of magnetic field that the spinons experience, and they experience cyclotron motion, and they have Landau quantization, even though it's an insulator. And so what's going on? So how to understand that? I realize there is a title here. This should have been J equals curl M. Sorry. So we have this statement that the currents are equal just because they have to move together, the spinon and the chargon. Current equals curl of M. So that is, you can translate that into a statement that the magnetizations, okay, have to be equal. Electron, spin, and chargon, they are always moving together. So when you apply a physical magnetic field, an emergent gauge field is induced, okay, of the internal gauge field of the system, this little b, such that the total field still splits. So the sum is capital B. This is splitting of the vector potentials that I was describing. So the total is always B, but the spinon experience is a fraction of it, and the chargon the remainder. Okay. And so you have some susceptibility for the spinon, some susceptibility for the chargon, equal these two equations that come from these statements of equality of currents. You conclude that there will be generically a finite internal emergent gauge field when you apply a physical field that depends on some constant that relates the susceptibilities of the two systems. Okay, but the statement is that it will be there, it will be finite. Okay.
I don't know whether, and
okay,
can I help you
charge transport, it will look metallic sometimes when you apply physical magnetic fields. Okay.
Can you interrupt for a second?
Of the magnetization. Because the magnetization is just the derivative of the free energy with respect to field. So when you apply field, there is this induced field, the spinons will be executing cyclotron motion. When temperature is sufficiently low, you will have Landau quantization of that cyclotron motion, and quantum oscillations. So there will be differences with a metal. So for example, the period will not be of the Shushnikov-de-Haas effect, will not be the area of the spinon Fermi surface, because there is this proportionality constant here that I'm here denoting by alpha. It's the same number. Okay, so you still don't know what that number is. But the idea is that there will be some some period of quantum oscillations.
I think Chinyao tried to raise his hand on this.
Yeah. Sorry, can you hear me?
Yes, try to speak up a bit, but
I can shout. Can you hear me now?
yeah, that's it.
Yeah, okay, good. Sorry, I decided to be distant. I always thought that the thermal conductivity, for thermal conductivity, the Ioffe-Larkin rule is not that clear cut. Can you?
Yeah. Oh, I see. You mean this statement right here?
No, just you had this conductance in series for the electrical conductivity. And I was just wondering whether you could remind me about.
Yeah, so for thermal, you should not do it, right? So it's only for electrical, because so let me see if I can say how.
Because the electric current couples linearly to A, right? When you assume that the vector potential is your U1 gauge field, where thermal current probably.
Yeah. So there is no Ioffe-Larkin rule for thermal conductivities. Everything carries heat, right? So it's.
Yeah, I mean, even.
It can be just carried by the spinons without having to physically create local density fluctuations in which you would go away from the constraint. Right, so
no, I mean, I think physically probably you're right, but formally,
how to see it?
I always found it very.
I mean, one would need to do an argument of how to.
This is a Matheson rule, right? You're adding resistances, but if you have more channels for thermal conduction, you should be adding conductances.
Yeah. So the point is that the statements about charge conduction come in the end from the existence of a physical conservation law, a U1 conservation law particle number. Okay. That's the core of where those statements in the end derive. For heat, there is not such a U1. There's no way to that I know that you can make it a U1, arising out of some underlying U1 symmetry.
Yeah.
Conservation of energy. So you really need to think of a new setting. Okay. I wish I could tell you more sharply, like, why it doesn't, but clearly you cannot pass it through the same logic because there is no U1 field for the heat.
Mm. Okay, so it's a delicate issue.
Yeah. So the Joffe-Larkin rule will apply when you have a part on the composition that has a U1 emergent gauge field and a U1 physical symmetry.
Mm-hmm.
The U1 physical symmetry is electron number conservation in the end. Okay.
Yeah.
So
But for the heat, there is not that structure, so you
Yeah.
cannot pass it through the same logic.
So what determines the size of the spin-off Fermi surface?
In the setting that I said, it would be just half of the brilliant zone, right? Because it's just, remember, the filling was half filling, so that you can make the insulator for the chargons. Then the size, the spinons will, they are also half filled, they will have to have half of the brilliant zone.
So that the crystal structure actually matters, right? Whether your zone will be quite different if it's a honeycomb or
Yeah. Like the
triangular.
detail of what is the Fermi surface will depend on which crystal lattice you are. Energetics, right? The energetics of the statement, the state that I haven't even touched, right? But whether you can make it, whether you're even allowed to make it, let's say, is kind of what I was sort of focusing on there. Yeah, very good. So, right. So there is some modification to the Lifshitz-Koszewicz formula. So, they have quantum oscillations. It's sort of a very simplified statement to say that they look like metals, right? So it's not quite the same. There is a modified Lifshitz-Koszewicz formula for the dependence of the amplitude of quantum oscillations as a function of temperature, etc. But, at some big picture level, they kind of look like metals, okay? For purposes of quantum oscillations. Let me not get too hung up with mixed valence insulators. This is too controversial. I want to move on to ruthenium chloride. So, but yeah, maybe just to say, there is some possibility that it's there in some mixed valence insulators. Okay. Yeah, another interesting consequence of these statements that I made is that they will also have some form of cyclotron resonance. Okay, this is actually something that has not been tried. So it's some proposal we made a few years ago, because the Spinon Fermi surface state is actually not a dead insulator. Okay, so I was telling you it's an insulator. I was just making statements about the DC conductivity at zero frequency. Okay, but when you start shaking the physical electric field at some frequency, people argued several years ago, it actually has a power law at very small frequency. Okay, it's not a dead insulator. There's no sharp optical gap, okay, for absorption. So it's some kind of soft insulator. Okay, it's some kind of soft insulator. And this all follows on the Joffe-Larkin rule. But once you realize that there is a soft insulator, and the fact that there is induced magnetic field is not very hard to imagine that there will be some cyclotron resonance. So we worked out the theory here. There's one interesting twist to the cyclotron resonance with respect to metals, and it's that it's always missing the Kohn mode. Okay. The reason it's missing the Kohn mode, so the principal, what would be the principal mode of the cyclotron resonance in metals, the omega C mode, is that that's mode is associated with, that mode is very strongly coupled to the gauge field. So it essentially becomes heat, and it's part of this large energy scale of the mode lobe, okay? But all the other, because the Kohn mode is associated basically with global displacements of the Fermi surface. This is meant to be a cartoon in which the dashed line is the equilibrium Fermi surface, and this circle is a slightly displaced distribution of the quasi-particles, and they are, you could view the cyclotron resonance in some, sort of Fermi liquid collective picture in which is just some oscillation of the total Fermi surface. But this mode in which the total Fermi surface displaces is very strongly coupled to the gauge field because you're shifting the center. Whereas the higher harmonic, this kind of elliptical deformation of the Fermi surface is actually, you can think of as the resonance responsible, the kind of deformation responsible for the 2 omega C mode, That one doesn't shift the center, so it's not as strongly coupled to the gauge fields, and so that's why these higher harmonics remain soft. They remain low energy modes that you can shake with cyclotron resonance. There is also some way that we propose to how to detect it with using noise magnetometry. Anybody has any interest in noise magnetometry here? Oh, very good. So, but this is kind of MB center noise magnetometry. But let me tell you the quick story. It's actually a really amazing story. Okay, so the transverse conductivity of a metal, of an ordinary Fermi fluid, okay, Fermi liquid, in the quasi-static limit, so in the limit in which you have finite wave vector but zero frequency, it's a universal quantity that only knows about the shape of the Fermi surface. So only knows about the radius of the Fermi surface. Let me put it here for a circle, but there is a generalization in which you measure local radius of curvature in general. So it only knows about fundamental constants of nature and the size of the Fermi surface. And this remains true even for strongly interacting Fermi fluids. There is no renormalization to this response function, okay, by interactions. And doesn't even know about the quasi-particle mass. It has no dynamical information, only geometric information of the Fermi surface. You can do the same calculation for the Spinon Fermi surface state. And what you find is that it also sort of has the same geometric information, but times a square of the same prefactor. This is the same universal prefactor that controls the ratio of the physical magnetic field to applied magnetic field. So apart from that prefactor, it's also universal. Okay?
So this is the order of limit Inti that's opposite to what we usually talk about.
This is the opposite one. This is the harder one because you are at finite Q and you have to come down in omega. You have to go inside the particle Hall continuum. So it's very tricky to probe this with usual kind of optical or near field, or it's very tricky to probe, but it can be probed with MB centers, because MB centers are basically spin qubits, okay? And so they are very sensitive to noise, right? So you just prepare the qubit in the excited state, and the decay rate of the qubit is controlled by how much is being shaken by fluctuations of the magnetic field around. And so if you put it next to the Spinon Fermi surface, there will be some quantum fluctuations of the current. Those quantum fluctuations are controlled precisely by this conductivity in that limit. Essentially, you can make an argument so that that noise will measure that size of the Fermi surface. So this noise will look metallic in an insulator. So it would be also a very sort of strong smoking gun evidence of this thing. But just to kind of close this traditional part of the Spinon Fermi surface state, this is still an open problem to really find good, strong experimental evidence, really smoking gun experimental evidence for the presence of this state, I would say. And that's why we have been thinking about all these, interesting sort of probes that could really tell you something, very, 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 very sharp qualitatively that you would not expect to see if the system would be, a dirty insulator, let's say, just a messy insulator. Okay. So just to summarize this first part, yeah, so the Spinon Fermi surface state is an insulator that sometimes resembles a metal. You can have quantum oscillations when you apply magnetic field in the magnetization and other quantities, especially the neutral ones like specific heat, for example. It will have some analog of cyclotron resonance without com mode. And it's not the fluctuations of magnetic field outside of the sample, the noise, the magnetic noise resemble those of the metal, that those you could probe with a MB center with a spin qubit. Okay.
Can I interrupt you?
Yeah, please.
Yeah. So the usual U1 formulation or equivalent sort of has was geared towards a metal, right?
Mm-hmm.
And so one could, in principle, connect with, as you said, that energetically, this particular trial wave function of the spinons and charge-ons, they are favored in some way. It's not a very clear-cut statement, but that's the assumption. But now, going to the insulating case, is there still a justification along such a line energetically?
What do you mean exactly? Like justification in the insulator?
Well, as you said, the trial wave function would be some kind of U1 for the Spinon Fermi surface direct product with some feature, some wave function for the charge carrying part, right? And you do some projection to take care of the physical constraints, the interactions. And are you basing the assumption that in the insulating case, or maybe perhaps closer to the Mach transition, that such a wave function still describes the favored ground state?
Yeah, that wave function I think should capture the universality of the state, let's say. But whatever should be universal about that state should be there in that wave function. Of course, you know, details always matter in the end, but some sense the universality should be there in that wave function.
But I mean, I guess maybe I can backtrack. I mean, one could imagine all sorts of spin liquids and other phases on the insulating side.
Right.
Why would this particular one be chosen?
Yeah. You know, I never touched the harder question that you are asking me, which is why is this the ground state of an actual Hamiltonian?
Right.
So that's very tough, you know, and I think for this particular state, it's extremely tough. So the only thing could be numerics, serious numerics, right? And there is still some debate even in which ideal models is realized. In the triangular lattice Howard model was for a while a kind of a serious candidate. There's now some current debate, which is still not settled of what is the ground state past the Fermi liquid, let's say, but still not too insulating before you go into, let's say, the Heisenberg antiferromagnet, the 120 degree. There's some very good evidence that there is a spin liquid, I think. Okay, some reasonable good evidence from numerics that there is a spin liquid, but there is still a debate whether it's, you know, a chiral spin liquid, for example. Still, I think this is a reasonable, the spin of Fermi surface state, but it's I think far from settled. Okay.
Right. Okay, fair enough. Yeah, thank you.
Okay. Yeah.
So can I ask, since you didn't give any Hamiltonians,
so
what
Hamiltonian is ... That's a joke by Santi. Hamiltonian is ...
Yeah. So what kind of interactions are we assuming?
Yeah. So you know, just to what I was telling Chimia, you know, okay, maybe if you want to have some model that is very reasonable, people tried. You just take the triangular lattice Howard model. Okay, at very small t, you will have a Fermi fluid, right? At very large u, you would have the 120 degree order because it's reduces to Heisenberg. In between, there is some kind of spin liquid, right?
Yeah.
There is still debate, as I was saying, what is that spin liquid? But people did some very extensive DMRG studies of a few chains in which they added extra terms to that Hamiltonian, some ring exchanges to that Hamiltonian, in which it looks like it's reasonable to expect then the spin of Fermi surface. So there's some model in which you could induce it, but it's very tricky, right? Because this is a gapless state with a Fermi surface. The evidence in numerics is even very, very tough.
I see. Yeah. Okay, thank you.
Yeah. Very good. So let's move on to the second part, or unless there's any other comment, question, please feel free for the first part. Right. So then the second part, so what I was telling you about is, you know, the traditional spin on Fermi surface state that, you know, goes back to Anderson. So now this is about a new kind of spin on Fermi surface state, okay, that has different rules, okay? So I will try to convince you. So this is inspired by some recent experiments in this material, alpha ruthenium chloride, okay? So very briefly, just to give you a kind of overview introduction of this material, okay? So this alpha ruthenium chloride is a van der Waals layer material. So for practical purposes, we will view it as a two-dimensional system. Okay? You can think of layers, very weakly coupled layers that have, you know, a hexagonal lattice of octahedra. Each of these effectively reduces to a spin 1/2. So it's a spin 1/2 in each site in each of these red dots in a honeycomb lattice. This material was gained a lot of attention because it was proposed several years ago that it's a good candidate for realizing something close to the ideal Kitaev model. Okay. But then, when people did experiments, they realized that it ordered. Okay, so as you lower temperature, measure specific heat, this red, orange dots are ruthenium chloride. It has a very clear peak in the specific heat, about 10 Kelvin. So it orders, and it's believed to order into this kind of zigzag antiferromagnetic state. Okay. Now, so that was a bit of not nice that it ordered, but then people kept investigating the phase diagram, and so when they applied an in-plane field, okay, field in this plane, they saw that the nail temperature went down, and eventually some region in which there was no sign of order appeared before the material would reach what people believe to be the spin polarized state. So there is some window of magnetic fields in which there was a good chance of a potential spin liquid. Okay, so one of the proposals that gained a lot of attention, or one of the experiments that gained a lot of attention, was the one that reported that there was some quantization of thermal Hall conductivity. Okay.
I thought this is not reproducible, right?
Yeah, this is not reproduction. This is not going to be the.
Okay.
I'm not going to use it. Don't worry. So yeah, that's still very debatable. So I'm being recorded, right? Actually. No, I think that's it's very still under debate. Okay. So. But more recently, okay, much more recently, something very interesting came up. Okay. So people were initially, this group, which is a group by Puanon in Princeton, they were trying to see evidence of quantization. They didn't see the quantization of thermal Hall. So this is kind of the region where the thermal Hall quantization was expected to be seen. The lower temperature just keeps going down. There's no sign of a plateau. Okay, some bump, but no sign of a plateau. Okay, so they didn't see the evidence for the quantized thermal Hall effect, but they saw something really amazing, and that is there just in the raw data. Okay, there's no data analysis. This is raw data of raw. I mean, your experimentalists know, but this is the actual data. Okay, so very clear oscillations of the longitudinal thermal conductivity. Okay, superimposed on some kind of dependence from background, but on top of that, very clear oscillations. Okay, very clear oscillations of kappa x. And this is also part of the controversy about the quantization of kappa x. Why I want to highlight the difference in order of magnitude. Okay? The kappa x, this is a thermal metal. It has a lot of heat conduction. The kappa xx is 3 orders of magnitude larger than thermal Hall. This is a tiny thing. Okay? This is a big thing, and it's visible in the naked eye. Let's say. Okay, oscillations. And more amazingly, these oscillations, when you plot them as a function of 1 over b, right? You plot the maxima, let's say, of the oscillations as a function of 1 over b, so that you're doing sort of the usual analysis that you do when you should think of the Haas oscillations for a metal. You see that their periods scale as 1 over b. They're linear in 1 over b. Okay, so the oscillations look like.
So this the field direction is in plane?
In plane. Yeah, this is very important. I should emphasize it even more. This is even more weak. It's not out of plane. It's in plane. It's all in plane field.
In which direction in plane?
They will be seen in both directions, but these ones I think are in this A direction. Okay.
I mean, do people know the magnetic structure? I mean, in plane, for that particular field?
Here, here is nobody, where the debate is, and this is where the oscillations are being seen.
But I thought it looks like it extends to lower fields.
It
right?
extends, it penetrates. So yeah, it's a maximum of the oscillations over this region, and it seems to have some penetration into the
Or the ferromagnet. I mean, the magnets can transport heat as well, right? I mean, How do you exclude that? I mean,
Well, how do you explain that magnums have 1/b periodic oscillations?
yeah, that's very strange.
Yeah. The envelope and so on, there still could be lots of complex things there that, but the oscillations are just very striking, okay?
On giving, we invited to talk about this at the March meeting, if you want to dig it out and watch it.
Yeah, I heard on giving a 1 hour talk on this.
Yeah.
I mean, I was very impressed, but I was just curious, but I wasn't paying particular attention to. Okay, well, go ahead, sorry, yeah.
But wait, Inti, is it true that primarily the kappa XX, the main contribution is from the phonons? At least,
I mean,
if there's
the envelope, will have the phonons will be a big chunk, right? And the envelope, the phonons will be there.
I mean, if there's a very strong, electron.
The absolute
phonon coupling,
value, let's say.
if there's very strong electron phonon coupling, I mean, a spin phonon coupling, spin lattice coupling. I mean, I don't know, but I still know
Phonons
why
will be
we
there,
offer it.
contribute to thermal conductivity, but why would they give you 1/b oscillations?
Yeah, that's very strange. I would agree with that. Yeah.
Right. So, and here is the thing, right? So, okay, oscillation. So the first thing that came to my mind, oscillation, the Spinon Fermi surface. So let's see if it works, right? And it actually doesn't work. That's why I have to introduce a variant of this thing. Okay? This is a very sharp reason why the Spinon Fermi surface doesn't work. Okay, so there's oscillations. We just talked about traditional spinon, the story I told you. Maybe this is the good old Anderson Spinon Fermi surface state, I thought. But then something very weird happens when you really analyze these oscillations in detail. Okay, that made me eventually move away from that hypothesis of just the usual Spinon Fermi surface. So first of all, as you were asking, the oscillations are induced by in-plane field. It's just literal in-plane field. You can also tilt the field and see whether the period changes with the out-of-plane component. And it doesn't. The period only depends on the projection of the field into the in-plane. It's largely, let's say, it has some small change, but largely independent of the direction. So there's different dots for very different angles from purely in plane, and you still see the same slopes. Okay, they are just shifted by clarity.
Actually, so the other question I have: Do people know that for in-plane field, how does the field change the domain population? Because for the A-type zigzag structure, you clearly have 3 domains. I mean, when you find in-plane field, for sure, or modify the spin, domain population. I mean, do people know how this happens?
Short answer is I don't know.
I don't think. I mean, it cannot be done. I mean, it's very difficult to do. You have to do neutron scattering to figure this out, but it's going to be very difficult.
Right. I don't know. What's the short answer?
Yeah.
Right. So the in-plane, the field, the in-plane field induces oscillation in both directions. I want to also emphasize that there is oscillations for when H is, in plane along B, in plane along A, and it's independent of the component out of plane, largely independent.
But when you apply CX field, then there's also
no oscillations. Right. So the oscillations are seen by in plane, and they are controlled by the component of the field along the plane.
Can you suppress the magnetic order?
Yeah, you can kill the antiferromagnet eventually. You have to go to much higher fields, I think, but eventually you can kill the antiferromagnet within.
Yeah, but see, if you apply a CX field, the domain population will not change. That's the key difference.
Okay.
well, it's conceivable that maybe if somebody puts it in 40 Tesla field, maybe one would have seen oscillations for.
I mean, I would be much more convinced if you apply CX field and see the oscillation.
No, sure, that's what you would want. That's what I would want to see, because that would tell me, oh, it's usual Spinon Fermi surface state. But this, this is the beginning of why we need to give up the usual Spinon Fermi surface state, because it's what the heck? Why is the out of place? The whole story I told you at the beginning was pure orbital magnetic field. So cyclotron motion and so on. So what's going on? So this is the first warning sign, let's say. But there is even something much sharper that tells you this is not the usual Spinon Fermi surface. So this is a very big warning sign that is in plane. Okay. But the sharper thing is actually a very precise symmetry argument, okay? When you apply field along the B-axis, okay, this is the B-axis, you see oscillations, as I told you. But when you measure the thermal Hall effect, when the field is along the B-axis, the thermal Hall effect is 0, within experimental uncertainty. This figure that I showed you at the beginning with the bump, that was for A. This is thermal Hall when field is along B. Okay. This is almost a contradiction if I assume that there is a spin-on Fermi surface state. Because suppose, that somehow the spin-ons, this emergent field is ultimately something that lives in the material. Imagine that it has some kind of weird coupling that it is induced by an in-plane field, even though it's not collinear, okay? How could I explain the coexistence of these two features? That's contradictory in a sense, because this is telling me those particles have Landau levels. They have some kind of Landau quantization giving rise to oscillations, but they don't have Hall effect. How can they not have Hall effect? By symmetry, the usual field in electrons, if you have quantum oscillations, you have to have some Hall effect. It cannot be exactly zero. Zero is too fine-tuned, okay? And there's a very good symmetry reason in the end why it's zero, as I'm about to tell you. So the reason is that when you apply the field along this B axis, there is a mirror plane. Okay, mirrors, turn clockwise motion into counterclockwise motion. So mirrors prohibit the existence of thermal Hall effect if they are present. If the ground state does not spontaneously breaks this symmetry, that would explain the absence of thermal Hall. So it's very natural. When you apply it along B, this mirror is broken because the field is a pseudo-scalar, right? So fields are not reflected, the component that is orthogonal to the mirror remains the same after a mirror because they are pseudo vectors, okay? Component that is along the mirror reverses. So it makes sense that when you apply along A, there is thermal Hall because you're breaking the mirror that would distinguish, counterclockwise from clockwise, but it's there when you apply orthogonal. So the experiment is telling you, you are applying the field and this mirror remains a good symmetry of the ground state, okay? But how would you have then emergent magnetic field and cyclotron motion for the spinons? And so this is where you need to change your spin, okay? So this is an implicit assumption that is forced onto you more or less by the Slade boson representation, which is the transformation laws of the spinon under mirrors mimic those of the electrons, okay? Because the chargon is featureless. So all the point group symmetry is swallowed by the spin, okay? So the spinon transforms like an electron under mirrors. In particular, the particle number, the gauge charge, the particle number is even. An electron doesn't map into an anti-electron by a mirror. Particle maps into particle. Particle number is even under mirrors, okay? And that is, once you gauge this, that immediately implies that orbital magnetic fields out of plane would have to be odd. So they are canceled by the symmetry, okay? But this is forced onto you by this Slade boson representation. If somehow this spinon was a different kind of spinon, not the spinon of the Slade boson representation, but it would be a spinon that would be particle Hall conjugated by the mirror, a spinon-like particle maps into a spinon-like antiparticle, so to say, or Hall by a mirror, which is very weird because, from the point of view of how electrons transform. If it would have that weird transformation law under the mirror, then the spinon particle number will be odd, because it's particle Hall conjugated. So the charge is odd. So charge is inverted by the mirror, okay? And once you gauge this, once you couple it to a gauge field, the magnetic field will be even. It would be a scalar. Let me give you a very simple analogy of why this is possible. Think about like Landau levels, okay? Composite fermions. Composite fermions, their effective magnetic field is the deviation away from half filling. So the magnetic field the emergent magnetic field that composite fermions see is electron density because it's something that measures. So it is a weird magnetic field, the one that composite fermions see in quantum Hall. It satisfies this kind of transformation laws. The magnetic field is like a density when it comes to mirrors. It does not reverse. It's not a pseudo-scalar for composite fermions. So it is as if this particle wants to transform, having this transformation law that it wants a particle Hall conjugate under the mirror. Okay, and so if you have that, then, by the way, how much time do I have left?
Yeah, no time left.
Zero? There have been a lot of questions.
Okay, let me try to wrap up in like 5 minutes, okay?
Andrew has been very nice.
So if you have the transformation law for the spinon, then basically what you will have in the end is that the emergent magnetic field will be even under the mirror and it will be allowed, okay? And how can you have in the end quantum oscillations and no thermal Hall effect, right? You know, the idea is that this spinon pocket, when you mirror it somewhere in the brilliant zone, you also have to particle Hall conjugate. So the implementation of the symmetry at the level of the dispersion of the spinons looks like this. There is a particle-like pocket somewhere and a Hall-like pocket somewhere else, okay? Something like this. And they are exactly compensated, you know, and exactly related by symmetry, by this mirror symmetry. So when you lambda quantize, you will get Hall-like lambda levels and electron-like lambda levels. They will be dispersing in opposite directions. You know, they will be moving in opposite directions as you increase the magnetic field. So there will be quantum oscillations because they are crossing the chemical potential. But there is a compensation by symmetry. So there is, you know, spinon particles experiencing, let's say, you know, clockwise cyclotron motion, compensated by an equal amount of Hall-like spinons doing the opposite. Okay, so that gives you zero thermal Hall effect. There is no net chirality for the Hall effect. It's balanced by the symmetry, even though there is oscillations of the density of states near the chemical potential, if you wish, as you change the magnetic field. Yeah, so that's the essence of it. I'm completely out of time, so maybe just to throw it for the experts in case somebody wants to catch me. You know, I gave you the intuition, but there is a way to make this very precise using a different Parton representation that is also, you know, well known but different from the slave boson, which is this abricosal fermions in which you just break the spin into two fermions. And the reason is actually very simple. So when you are at half filling, okay, when you have some lattice and there is, you know, one particle per side, when you're exactly at half filling, so that you just have, you know, spin moments at every location, there is two physically equivalent ways to represent a mirror in this slave particle representation, right? So the physical spin, you know, imagine you have some Heisenberg-like mode, right? And you have a mirror. So the physical spin has to be reversed by the mirror. And there is two ways to represent that with the particle, once you break it into these particles. One is, you know, let me imagine I have these two dots are whether I'm filling, you know, one of the two states, one with spin down or one with spin up, right? So there's one in which I just reverse the labels that I'm assigning to each of the dots, right? So the particle here didn't change, you just reverse it, the spin to us. That's how it gets implemented in electrons, okay? But there is a different way in which I just, you know, remove the particle from the occupied state with spin down and put it in the one with spin up, okay? Physically, I'm doing the same, you know, filling at the end, spin up. So it's the same physical, the spin operator is still transforming in the same way, the same physical symmetry, but in technical levels, it has different projective, it can have two distinct projective symmetry group implementations in this abricosal Schwinger fermions, one in which is particle Hall-like and one that is electron-like. And so this will be two distinct, sharply distinct phases of matter that have different projective symmetry groups for implementing the symmetry. Okay, so there's some very precise way to do this with sort of the language of projective symmetry groups and abricosal fermions, and write down a good Ziegler wave function, enforce all symmetries of ruthenium chloride. And so you can come up with some field state, you know, possibly, you know, I don't have very good reasons for energetics again. Possibly these spinons could be small pockets that are located at the endpoints of the brilliant zone because those are the ones that are connected, but the wave vector that is associated with the formation of the same antiferromagnetism. And this is why probably the oscillations survive to some extent inside the antiferromagnet. The spin liquid and the antiferromagnet are very closely related. The antiferromagnet is some kind of particle Hall instability of the spin liquid with these pockets connected by that wave vector. That's sort of the proposal, okay? So let me just close with a summary. Yeah, so just to summarize, very, you know, interesting, strange quantum oscillations of the thermal conductivity kappa XX that sometimes are accompanied, even though you have oscillation, zero thermal Hall effect, you know, cannot be fit within the traditional Spinon Fermi surface state, but it might fit within this new kind of Spinon Fermi surface state in which the spinon is particle Hall conjugated by some space symmetries of the lattice. in particular this mirror, okay, that forbids the particle Hall. And so this allows you to have Landau levels without Hall effect, so to say. It's a symmetry that kills the Hall effect, but does still allow you to have Landau levels. And this gives you sort of a universal, at least, mechanism for how to explain this kind of observation. Yeah, that's, thank you guys.
So do people understand why a CS field is so hard to suppress the order?
Don't have a very precise statement, but yeah, so I don't.
I mean, also,
But-
there's no oscillation, right? along
No,
this?
there's no oscillation, but it certainly has
But
less.
like, from your picture, how do you understand that? I mean, that's probably easy.
Oh, yeah, so, I never told you what is this field, okay? So I never told you really what this emergent field is. So that emergent field, it is actually a physical thing, okay? So in the sense that in the traditional Spinon Fermi surface, this field, this emergent field is a kind of measurement of the, even though there's no long range order, there is some kind of spin chirality that appears. Okay, the spin operators acquire certain chirality. So there's some operator that you can make out of 3 spins that acquires expectation value. And that's sort of the physical meaning of the field. That operator has certain symmetry transformations. In particular, that operator is chiral. So as soon as it acquires value, the system can have Hall effect. Okay. This physical field, which I don't really understand what is made out of in microscopic, detail of spin operators. Really, I just know like a very general symmetry argument must have some behavior that is non-chiral. So it could be that it's something like I feel. I mean, this is a part that is a bit more like say loose thinking, but it could be related to some kind of operator that measures the local tendency of the system to make a spiral magnetism. Some spiral magnetism, but still without long range order. So the field is, if you wish, in a sense, like the pitch of the spiral. The operator is trying to measure how much the spiral pitches. Okay. So all I'm trying to say is there is some physical understanding that this field would have to have that I still need to develop to really understand how it couples to the physical field. But the idea in a sense is you apply the physical field, right? In plane, and then this spiral, for example, imagine it was this kind of story I just told you, the tendency to do the spiral correlations changes continuously as a function of field. There is a pitch of the spiral that is changing with the in-plane field. So, but what happens when you apply out of plane field is completely different because it's, how does a spiral respond to an in-plane field versus an out of plane field? So something like this, but this part is a very vague thought that's still under development.
No more question?
Maybe- Can I ask one more question?
Yeah, please go ahead.
So do you differentiate between the quantum oscillations seen in the magnetization versus in transport?
No, they should be related. So in my hypothesis, let's say there will be quantum oscillations of kappa XX, and there should be similar quantum oscillations concomitant in the magnetization.
Mm-hmm.
Yeah, it would be in-plane magnetization, right? So because in-plane magnetization, this actually had something of this, but I didn't have much time, should have oscillations. Yeah, here we had some prediction for the in-plane magnetization oscillations should be there with this accompanying these oscillations of kappa XX.
Okay, yeah, thanks.
In the end, it just follows from magnetization being derivative of energy with respect to magnetic field. So once there is Landau quantization, magnetization will also have oscillation.
So do people understand? Can you show on state again? Do people understand why the oscillation becomes bigger when you only change the temperature from
Temperature dependence is quite non-trivial. So
Yeah,
this is something I didn't have a chance to.
When you only change it from 0.43
So let
to
me
1.7K, I mean, magnetically it's the same, right? What's the difference?
Yes,
Why it becomes smaller?
from Lipschitz percentage, right?
It does not follow Lipschitz-Kosevic.
Do people understand that? They don't. right?
No, there's no good explanation of the amplitude. So let me say the amplitude sort of decreases with temperature.
That's very strange, right?
But when you divide the amplitude by the background, which is what they are doing here, it grows. So the relative, you see, because everything is kind of suppressing, the thermal conductivity is suppressing as you lower temperature. So both the amplitude and the envelope, the background is going down, but there is a relative growth of the amplitude with respect to some kind of background. Okay?
Yeah, but
it's
thermal
very
con-
tricky. So it's not Lipschitz-Koszewicz. The amplitude, if it was just naive Lipschitz-Koszewicz, the amplitude alone should grow.
I mean, your amplitude, thermal conductivity for thermal conductivity for phonon thermal conductivity should decrease, right? It's decreasing time for sure because it's random, right?
Yeah.
But your magnetic thermal conductivity should not change as long as you have a decreasing temperature.
If it was just free fermions, let me put it this way: the theory of this could be very complex because it's a different kind of coupling to magnetic field, how the oscillations are occurring. But if it was just usual free fermions, the amplitude should just grow and saturate like Lipschitz-Koszewicz, and that's not what they are seeing. So just to say that is complex. What they are seeing is that the amplitude, as absolute amplitude, also decreases. So that's non-Lipschitz-Koszewicz. So it probably has some non-monotonic behavior. So eventually, it's zero. It's no amplitude at very high temperatures. It increases, and then eventually it starts decreasing again. It's non-monotonic.
Okay.
So your theory, so it has vanishing thermal Hall.
Along one direction.
Okay,
Along the other direction, because the symmetry is broken, then you will
Okay,
have
okay.
finite.
I see.
Yep, one more question. Yeah.
So essentially what would happen if I would be able to, like I would just scan the angle between the two directions. So because the symmetry is kind of immediately broken, right? Would you expect some sort of crossover or?
Yeah, the angular dependence is something that has not been looked at, and it could be very tricky. But roughly speaking, there should be a zero when the symmetry forbids it, and then a maximum when you're sort of. This has like a 6 symmetry, and this has been seen in certain symmetry-related directions. So that's various zeros. So this A just, I just showed one A. Sorry, one B direction. But there is a symmetry-related B direction, at least rotated by 2 pi over 3. So maximum, then against minimum, or essentially zero with an experimental uncertainty. I mean, more maximum.
Would you be able to actually extract the let's say the function that tells me the weight of the thermal Hall, depending on the angle, because that would be kind of actually a test for your theory. Right?
Again, as I was trying to emphasize, the thermal Hall is the tiny.
Oh,
So doing theory of tiny things is inverse harder, right? So yeah, but one should be able. Let's put it that way. One should be able, but it's the small things. The small things, not the big.
but I mean, it's never always.
Right.
Awesome. Well, thank you so much. Let's thank Inti again.